Hello everyone, welcome back to the Cybertech YouTube channel. This is the next installment of the data structures and algorithm video series. So in today's video, we are going to talk about expression trees. So have you ever wondered if you type an expression like this in a calculator, how does this machine calculate this or process this? So there are many ways to start and many ways to calculate, but it needs to calculate the correct answer. So under the hood, the calculator actually doesn't read this from the left to right like we does. It actually creates a tree and hold these operators and operands on the nodes and then do the calculations. So for that they use these expression trees. So what is an expression tree and what are the purposes of it? Grab your pen and let's go back to the video. So if you are given an expression like this and you are asked to solve it, how do you solve it? So we actually have a set of rules declared among ourselves to solve an expression like this. Mainly two sets of rules. The first one is operator precedency and the second one is associative. So operator precedency basically means the order of the operators we are solving. In the precedency we have brackets at first, then the power of operator, and then division, multiplication, and then addition and subtraction. So this is the operator precedency of solving expressions. And then associative means whether you are reading the expression from left to right or right to left. So if in the power of operator we actually read from right to left. So and in the division and multiplication we have left to right. And then in the addition and subtraction too we have left to right. So using this set of rules, we actually can solve these expressions by ourselves. So before actually talking about expression trees, let me give you a quick summary about the tree data structures. So a tree is a nonlinear data structure which stores data on separate levels. This topmost node is called the root node, and the internal nodes are called the parent nodes. And then the nodes without children are called leaf nodes or the leaves of the tree. So in order to access the elements in a tree, there are actually three ways. The first one is in order, where it is when we are starting from the left node, go to the root and then right. And the next method is the pre-order. It is where we start from the root and then go to the left side and then the right side. The third way is the post order. It is where we start from the left, go to the right, then the root. So when in a tree, if all the parent nodes are having exactly two children, that tree is called as a binary tree. So what is an expression tree? If a binary tree representing an arithmetic expression, it is called as an expression tree. By arithmetic expression, I mean any kind of expression. For example, a simple expression like this. If we can show this in a tree or a binary tree, then that tree becomes an expression tree. Okay, so let's now go into the deeper theories of these expression trees. So in an arithmetic expression, there are two things, operands and operators. Operands can be final values, or basically numbers, or symbols like x, y. These are called operands. And then there are operators. Operators are addition, subtraction, multiplication, likewise. So in basic expressions, every operator should contain two of the operands. For example, if you are writing a plus, then there should be two operands. If you are writing a divide, then there should be two operands. This can be a value or a number. So how do you express these kind of expressions in a tree? So I will start from the human friendly methods and go into the machine friendly methods. So we have an expression here, and as you can see, we can easily solve it by, since we know the operator precedency and associativity. But in machines, it is a bit hard to include that precedency and associativity, and it is going to be rough even when the expression is very long and very complex. So data scientists has been introduced two more methods to avoid this precedency and associativity. The first way is called the Polish way, also known as the prefix expression. So in here, what happens is the operators comes before the operands. So if you were to write this 2 plus 3 in the prefix way, what you need to do is write this operator first and then the two operands. So another way is the PostFix way. This is also known as the reverse Polish way. As you can guess, what happens here is operator comes to the end of the operands. So if you were to write this 2 plus 3, you can write this as this. So in using these two ways, we can actually avoid the precedency and associativity, and it is easy for machines to do the calculations in this way. So before going on to constructing the trees, let's actually see how you convert these long and complex infix notations into the prefixes and postfix notations. So let's see how you can convert infix expressions into the prefix and postfix expressions. So the main idea that should be happen is the precedency and associativity issues should be tackled, and the parenthesis issues should be tackled. So I am going to use the stack logic here to convert this infix expression into the postfix expression. So what are the rules? If you found an operand here as the input, simply put that into the expression. But if you find an operator as the input, you need to check the precedency level of that inputting operator with the top of the stack operator. If the precedency of this inputting operator is higher than the operator in the stack, then you need to directly push into the stack. But if the inputting operator precedency is lower than the operator in the stack, then you need to pop the operator from the stack and then add to the expression, then push that operator. I'm sure you will understand that once we are done with this example. So let's start. And there are also special rules for the parentheses. If you find an opening parenthesis or opening bracket, you simply add that into the stack. That's it. Then I have an operand and I just included that into the expression. Then I found an operator. So here, even though I have an operand parenthesis, the rule is to check the precedency of the non-parenthesis operator. Here I have no other operators in my stack, so I just simply write plus here. And my expression still have number 2. Then I have 3. Again an operand. So this stack still same, and operands will go to the expression. Then I have a closing parenthesis or a closing bracket. So once you find a closing bracket, what you need to do is pop all the operators until you find the opening parenthesis. So here I need to pop this addition operator, and then I can find the opening parenthesis. So my stack will be empty because these two are ignored, and then my expression will be like this, because this addition has been popped. Then I have the multiplication. Right now my stack is empty, so I can directly enter that in. Next I again have an opening parenthesis. Again just push that into the stack. The expression will be saved. Then I have an operand. So now change, simply write the operand. Then I have an operator. So here on top of my stack is a bracket. We can just simply push that operator into the stack. And the expression will be same. Next I have an operand. Again simply put the operand on the expression. And then I have the closing parenthesis. I will write it here. So I have the closing parenthesis. So I need to pop all the operators until I found the opening parenthesis, which is here. Means I have to pop this addition. So my stack gonna be like this, and my expression gonna be like this. This is the operator which I popped. Next, my expression is done now, so I can just simply pop the remaining operator and create the postfix expression. So this is the postfix expression of this infix expression. Next, let's convert an infix expression into a prefix expression. So to do this, we can actually use the stack logic, but it is a bit trickier because we have to reverse this expression, convert into the postfix, and then reverse it again. But let me teach you a much clever and easier way to convert an expression like this into the prefix form. So what you need to do is, as you can see, there are sub operations of this expression, which is happening within the parenthesis, which is the highest precedency operator. So no matter what, these two should be happen first. And you know, in prefix the operators comes first, then the operands. So we can simply write these two as plus 2 3 and plus 5 4. Always the left operand goes first and then the right operand. So you can write this like this, and then again, as you can see, an operator with the two operands, and the operator comes first. So operator, the left part and the right part. So this is the prefix of this infix expression, a much easier and understandable way. Actually, in order to represent an expression in a binary tree, you only need to know about two rules. The first one is the internal nodes or the parent nodes always must be operators. So for example, the root also an parent node, so it should be an operator. And if this is a parent node, it should be an operator. And the leaf nodes, which means the nodes does not have children, must be values like this. So in these parent nodes there cannot be any values, and in the leaf nodes there cannot be operators. That is the basic rule of expression trees. So since we have an idea about infix, postfix and prefix expressions, let's go back to building an expression tree. So in order to create an expression tree from the infix expressions, we need to concern about this operator precedency and their associative. For example, I'm going to write an expression like this. So this is an infix expression which is close to the human language, and then I'm going to create a tree from this. So in order to create a tree from an infix expression, what you need to do is scan this statement from left to right and find the least precedency operator. So here, if you scan this from left to right, we can find the addition, multiplication and subtraction. Since subtraction is the least precedency operator, we can simply write that as our root. And from that operator, this whole left side gonna be the left subtree, and this is gonna be the right subtree. So I can simply write 3 here and keep it as a because this is an expression. So again, scan from left to right. I can find addition and multiplication. Since addition is the least precedency operator, we need to write that first. And from that addition, this is going to be the left subtree, this is going to be the right subtree. So I can write the 2 since it is just a leaf, and then the right subtree, again an expression, but here we only have one operator, so we can simply write the operator and then the child. So this is how you can write a tree or draw a tree from the infix expression. As you can see, the highest precedency operators will always be at the bottom and the least precedency operators will be at the top. Since we have the tree drawn here in the infix expression, let's see how easy it is actually to get the prefix and postfix expression from this tree. So as I said earlier, prefix means the pre-traversal order of the tree, which means starting from the root, then go to the left subtree and then the right subtree. So if we write the prefix or the pre-order of this tree, it would be starting from the root, again left side, root, left side, right side, and then the right subtree. So this is the prefix order, prefix expression of this infix statement. And in order to get the postfix expression, all we need to do is do the tree traversal but in the post order, which means starting from the left, go to right and then north. So here we write 2 and then 3, 8, multiplication, addition, 3 and minus. So as you can see, getting a prefix and postfix expression from an infix expression is so easy if you have the tree drawn for it. So you do not need to engage any of those stack logics in order to find it. You can simply do the tree traversal and get the expression you need. Let's discuss another problem about these expression trees. So here I have an prefix expression, not an infix expression, and I'm asked to write the infix and postfix. So we can simply get them by drawing the tree. So how to draw a tree into a prefix expression? It is actually very easy. All you need to do is in trees, operands come to the leaf nodes and operators comes as parent nodes. And the other thing is, prefix means the tree traversal order is pre-order, which is root, left and right. So simply you can scan this statement from left to right and put the nodes, operators as the parent nodes and operands as the child nodes or the leaves. So here we start from the root, then go to the left side, operator, go to the left side again, operator, go to the left side again, operand. Since this is an operand, no more child nodes. This is a leaf node. And then we go to, we need to put the 1. We go to right, put 1, go right again, put 2, go right again, put 3. And now we have the tree to this prefix notation. So it is actually very easy to draw it like that. And then it is again easy to get the infix and postfix. Infix means the in-order tree traversal. So as you can know, 5 plus 1, again multiplied by 2, again divided by 3. This is the infix notation of this prefix notation. So postfix, which is left, right, then root. So 5 1 plus, then go to 2, and then go to 3, and then find the root. Okay, so now let's see how these expression trees are built and evaluated in the codes. So for this example, I'm using the NetBeans and Java as my language, and here I have a class called node to store our trees, and this node class having values, and then left and right nodes to store further data, and then an optional function to type the tree or print the tree in order. So let's go to the code. So here are my two expressions, one in the postfix and one in the prefix. So let's take one by one and see how these expression trees can be formed from these postfix and prefix. First, to get an idea what this expression actually is, I can write this in order so we can have a better understanding. Since this is not a much longer expression, we can just directly write this as so for example, here I have 2 and 3 with plus operator, and then 5 and 4 with negative operator, and then I have the multiplication at last, which means this in order should look something like this. So this is the in order infix expression which has been converted into these two. So right now what we are going to do is create the tree to this expression. So let's go to that function. So this is the function to create a tree from the postfix expression. So let me actually get the expression here, copy that, and here paste it. So let's see how the tree is being formed. So here I have a stack in order to create the tree, which I also showed you before in the whiteboard using the stack logic. Here I'm getting the my data set as an array, as a string array. Here this is the data set I'm getting, and first what I'm doing is for every checking every data in the array from left to right, and if this is if the element is an operator, let me show you that too. So is operator is an simple function to just to check whether the element is an operator or not. So if the element is an operator, we have a function to do, but for now my first element isn't an operator, so what is basically happening is pushing the node into the stack. So let me draw the stack. So the 2 is pushed. Then for the next element, it is 3. It is also not an operator, so it is also pushed to the stack. And then it is plus. So plus is an operator. So what happened now is I'm creating two nodes from the node class as left and right, and on that variables I'm temporarily saving these two elements. So a very important thing to notice here is always the right should be the first one popped and the left should be the second one popped. So right, left and right here. So the first popped element, which is 3, and it should go to it should go to right. It should go to right, and the second one go to rest. So this is actually important because on the node we are trying to enter, which is the new node and the plus node, here this left property of this node always should be the left value we popped earlier, which means the first value we inputted. So the left and right should always be correct in order to tree to work. So like that we are saving left and right, and then we are going to push this entire node into our stack. So right now we don't have 3 and 2 anymore in our stack because we popped and we saved on this node. So right now our stack will be look something like this. This entire node will be in this, like this. This entire node will be in this stack. Moving on, right now we have 3, 2 and plus, then we have 5. So 5 is just not an operator, is operand, so we can push it here. 4, same, not an operand, an operator, so we push it here. Then again we have minus. Minus is an operator. Again we need to create right and left, and the first pop should be the right one, like this, and then the next pop one should be the left one. So my stack would be like this now. Then what I need to do is create the new node for the operator, which is minus, like this, and of this node the left property should be the left one here, which is 5, and the right property should be the right one here, which is 4. And now it push the entire node into the stack. So right now my stack going to be look like here, the minus 5 and 4, left and right. So my stack will be look something like this now. Let me delete that. Then so then I have the multiplication, which is again an operator here. That now I have to do is again take two variables, right left, pop the right one, pop the first one, which is this subtree, which has minus 5 and 4, and then pop the next one into the left variable, which is plus 2 and 3. Yeah, so my stack is empty now since I popped all the elements. And then what I need to do is take the new element as the new node, which is the multiplication, and make this right and left like this. So after that, when I push to the stack, it's going to be look like something like this. So I have the new node. On the left side I have the left subtree, which is the plus 2 and 3, and on the right one I had the minus, which contained 5 and 4. So likewise function will be executed until the all elements in this array we are getting stored in a tree structure. Next, build and tree from the prefix statement. So this is actually very easy because let me get this one first. What is happening in prefix is exactly same thing happening in the postfix, but here we read our array from right to left, not left to right. As you can see, this for loop will ensure that our first element will start with this final element, and it will go until all the element is the array will checked. So the inside operation is exactly the same. If the element is an operator, the two elements will be popped and it is saved as they are right, left and right. And if it is not an operator, it will be pushed directly into the stack as an node. And in the end, the tree will be built as the same as in the post order, because we read this from right to left, not left to right. That's how you create tree structures from prefix and postfix expressions. This simple function can do it. So next, let's see how you evaluate an tree or an expression tree. For this one, I'm using an postfix expression or an postfix method. Here I have this postfix array here. So first I'm going to make it as an postfix tree from this function, the function I showed you earlier, this function. So after this function, it is retaining the root of the tree, which contains the entire tree we built earlier. So and then it is redirected into this evaluate function. Let's see how that works. So let me first draw our tree, the current structure of our tree. So what we had something like this: 5, 2, 3, and here we had the minus, here we had 5, and here we had 4. So this is a recursive function to evaluate an tree. So here we follow the post order, and our base case is to find an operator and then separately evaluate the left part of it and the right part, or the left subtree of it and the right subtree of it. So if it is not an operator, then it will be passed into an integer, since all the values here stored as strings. We get the numbers as integers, check with the operator and evaluate them. So here first 2 and 3 will be evaluated, and 5 will be the answer. Here 5 and 4 will be evaluated with the minus, and 1 will be the answer. And finally 5 and 1 will be evaluated with multiplication. So the answer should be 5. So this function is done through this recursive function, and here we can see we can easily get an answer of a complex expression using these trees. So actually we can check it by running the program, and as you can see our answer is 5. So likewise we can get an evaluate an postfix expression tree from the simple evaluate function like this. So that's it guys for these videos, and I hope you understand what is this prefix, postfix and infix expressions, and how do you represent them in trees. Pretty basic concepts and very efficient ways of handling and storing mathematical expressions. And I hope you guys keep watching this video series in order to get more idea about data structures and algorithms. See you soon. Bye.